Okay, so welcome to the current hottest. We are happy this time to have Ambrus Kaposi from Utrecht University, who will be telling us about quotient, inductive types, and higher friends.
Yeah, thank you very much for the invitation. So I will present joint work with lots of different people. I missed some people in the abstract, so here is the hopefully complete list with whom I worked on this project. So my motivation for quotient inductive types was understanding type theory, and then because type theory is a very nice language, I wanted to describe what type theory is inside type theory, and that there these quotient inductive types come in. So the most traditional way to describe programming languages such as type theory is using simple inductive types, and this was done formally in Agda for type theory by Abel and Vetsosi. I will show you an example of this in the next few slides. You can also use inductive types, which give you an intrinsic representation of type theory. So compared to using simple inductive types where you define the language with syntax or pre-syntax, typing relation, and operational semantics, with inductive types you merge the typing relation and the syntax, and you only have well-typed terms, and you can describe the type theory in that way as well. And in fact, the motivation for introducing inductive types in type theory was this kind of intrinsic syntax of type theory, which was described by Chapman in 2009, and then in Fredrik Nordvall Forsberg's thesis 4 years later, they were given a precise description. And in fact, Agda already had inductive types before the name inductive type was invented. So it was a similar situation when with Thorsten we described the syntax of type theory using quotient inductive types, or QIITs. And that was 4 years ago, so now it's probably time to formalize what these QIITs are in general. So at this time there was no formal description of QIITs, and this talk will be about QIITs and some extensions. And other examples of QIITs are the real numbers from the HOTT book, or ordinal numbers, or the partiality monad. So the interesting thing about these QIITs is that they are all infinitary. We will come back to this later. So we can describe a simple language with dependent types as a QIIT, which only has context and types, but types are indexed by context, so they have the same shape as context and types in type theory. And we have two so we have two sorts, or two sets, mutually defined. So types refer to context, and then the constructors of this type, they can refer to both context and types. Like we have the empty context, which is just the context. Then we have context extension, which refers to a context and the type, and then returns a context. We have a universe with U and EL, or just some kind of simple thing which looks like a universe, and then sigma types. And we also have an equality constructor. This is a bit unusual, but maybe natural to say for this very small example that if I have a context gamma, then I extend it with A, and then I extended it with B. Then here I state that it is equal to the context gamma, which is extended by the sigma type of A and B. And this definition here can also be viewed as an algebraic theory, or a generalized algebraic theory, or it can be also transformed to essentially algebraic theories. So it's generalized because we have this indexed here, index here, and it's not just two mutually defined sets, but we have this indexing, and then the description of these theories becomes much more complicated. So if in the intrinsic representation, which I view as a one lower level representation as the QIIT, what we do is we still leave the context and types, so we still have only well-typed terms, but the equality becomes a relation. So the equality becomes an explicit, just like in operational semantics. So now, or equality, or it's sometimes called conversion relation. So here we have a conversion relation for context, and we could also have a conversion relation for types. Now it's trivial, but in a more complete example, this would also be included. And we have the usual constructors, or the point constructors are the same as before. And this sigma and context extension equality constructor is now not an equality, but it's a ordinary constructor constructing an element of this called con tilde set at the appropriate indices. And this is how we state equalities. And this is a lower level representation in the same way as you can have lower level programming languages in which you can write lots of non-well typed or non-well formed things, and here as well you can write lots of weird constructors of these relations, which should be equivalence relations, and you also need lots of extra boilerplate, which says that, for example, this is a congruence, that the empty context is related to itself, or extended context preserves the equality relations, and so on. And then this is what type theory looks like, or for this simple language of dependent types looks like in the most traditional representation, where we only use ordinary inductive types. So there are no inductive types, there are no QIITs here. So we have these preterms using, here I wrote it with this BNF notation, and then we have these four relations on these preterms or precontexts and pretypes here, and this part here selects the well-typed part, or the well-formed context and the well-formed types, and here we have the same equivalence relation. And I view these three different presentations as in the case of type theory, the first one is the most high level representation, and this intrinsic syntax and the syntax with preterms, it's a kind of implementation. So if you want to obtain QIITs, what you can, and you don't have QIITs in your language, what you can do is you just use inductive types or IITs to implement them. If you don't even have inductive types, then you have to use something plain inductive types. And for example, I think still now the only proof assistant which has inductive types is Agda. Maybe there is some experimental version of Bocquet as well. So most people are resorted to use this kind of low-level representation, and yeah. But now we have cubical Agda, and then cubical Agda has QIITs. So we can also already work with an implementation which has that. So in this talk, this was the motivation. And I will talk about the formal specification of closed IITs first, because that's a simple, interesting subset, or simpler than QIITs. Then I extend this formal specification to QIITs in multiple steps. Then I will talk about what results we have for the existence of QIITs. And then talk a bit about HIITs and an extension of QIITs to syntax with binding. So first, what are QIITs? So how do we specify a QIIT in Agda, or in general an inductive type in Agda? We write data, then we write the sort what the shape, write down the shape or the arity of the sort, and then list the constructors and give the arities of all the constructors. So this is natural numbers. Then we have integers here, which is a quotient inductive type. It has 3 point constructors and these 2 path constructors. There should be a third higher path constructor as well, but now I don't consider that. And we can also implement the previous example of context and types. So in Agda, we have some limitation because we have to list all the constructors for one sort at the same time. So I cannot say that I first list some constructors of context, then some constructors of tie, and then I would want to list this sigma, this equality, which relates some constructors of context and some constructors of types. So there are some tricks which help us solve this. So here I did a forward declaration of context extension and sigma type, and here I said that the forward declaration is in fact the same as the official one. So this is a trick to encode this into Agda. But the idea is that specification of a QIIT, and then Agda lets us, once we have specified the QIIT, then Agda lets us define functions by pattern matching on the constructors, which should be the same as the elimination principle of the QIIT. So the specification of a QIIT is basically the sorts and then the list of constructors. But you can see that it is not simply a list, because later constructors like this beta constructor can refer to previous constructors. So for example, I couldn't add beta before successor because of this forward reference. So it's not really a list. In fact, it's a telescope because it because of this dependency. Once we add some new stuff, we can already build from that new stuff when we build the later things. So that's
a question, Ambroise.
Yep. Yep.
Yeah. So to be clear, you're talking here about the cubical mode of Agda, right?
Yeah. This is in cubical Agda. Yes.
Yeah. And when you say we have the ability to define functions using pattern matching, that's not a full statement, but maybe it gives an impression that things are better than they really are. I mean, we have the ability to define various paths using pattern matching, but we, in doing that, have to solve some definitional constraints on the paths by ourselves. So the situation is not as good as it could be.
Yeah. So
well, hang on. What do you mean? I didn't understand what the concern is.
Well, to say that in Agda you can define functions, say on int, by pattern matching, to the uninitiated might sound like it was an easy sort of thing that was like pattern matching for, in the non-cubical part of Agda. But the fact is it's not that easy, right? Because you have to define paths. The paths have to match up on their endpoints, paths, cubes, higher cubes, and so on and so forth. And that can be quite tricky. So at the moment, Agda doesn't give you much help to solve those definitional constraints on the endpoints. You have to do it yourself, as it were.
No, but that's just, I mean, it's still pattern matching. There's nothing fundamentally different, right? I mean, you can always come up with a difficult problem. I mean, well, anyway, let's take it offline.
Yeah, but probably it could improve. And I think recently cubical Agda didn't support indexed inductive types.
Yeah, well, that has changed now.
But that's fixed by now. Okay.
Yeah. Anyway, we'll take it offline. Sorry.
Yeah. But this is so here I just wanted to illustrate that even the definition of a QIIT is not very simple, because it's this telescopic definition. And the idea to define signatures, we could try to describe what these telescopes are by hand, but we already have a tool we already know a tool which is exactly for describing this kind of intricate dependencies, which is type theory itself. So, and I think I saw this idea earliest in Jacques Carrette and Russell O'Connor's paper in 2012. and I can't remember the title now, where they defined signatures also as contexts in a type theory. So a context is a telescope of types, or as a closed type in type theory. And so we have a handcrafted type theory, which we call a theory of signatures, which is exactly designed for describing these QIIT signatures. So it has now I show what it looks like for closed IIT signatures. So we have this, we start with categories with category with families, which is the substitution calculus part for type theory. So we have context, substitutions, types, and terms. We have the instantiation of a substitution, so we can substitute types and terms and so on. We have context extension and all of this structure. And then what is specific, so this doesn't come with any type formers. And then the specific type formers for these closed IIT signatures is a universe with U and EL. So it's a Tarski universe, but it doesn't have anything inside, so it's empty. And then we have pi types, where the domain is in the universe, the codomain is an ordinary type, and then the pi type itself is an ordinary type. And we also have application. We could also include lambda, but in the most minimal version of the theory, we only have application and nothing else. And we will, and with this small type theory, we can already describe closed IITs. By closed, I mean that we cannot describe lists, for example, because lists refer to some external type because they are lists of something, or vectors which are indexed by natural numbers, so they depend on natural numbers. And we also don't have equality constructors yet. I will show you some examples. So later we will add more type formers, and each additional type former will give us a possibility to describe more kinds of inductive types. So for example, how do we write natural numbers? So a signature is a context. So this is how we write it formally. So we start with the empty context, then we extend it with U, then EL of Q. So Q is the 0 de Bruijn index, and then we have a function space, but I will write variable names for readability. So this is just the context in which I have a type, or n colon u, then an element of it, which is 0, and then I have successor. And so here I need to write a type, so I need to decode this element of the universe, or this code in the universe n. And when I write a function, there is an asymmetry, because on the left-hand side of an arrow, I always need to write an element of u and not a type. So I cannot write here an arbitrary type, only an element of u. And on the right-hand side, I can write an arbitrary type. So this is why I need to write n arrow ELN. And this is what enforces strict positivity of all the constructors, because on the left-hand side of the arrow, I cannot write an arrow, because the arrow itself is a type and not an element of u. And I can also describe inductive types this way. So this is a fragment of the previous con-tie example with context and types without the equality constructor. So I can use the same function space that I use to describe the successor constructor here. I can describe with the same, so I can use the same one to describe the indexing of types. So types for each context, I get a u, I get a type, then I have the empty context where I need to write EL, and then this is the application operator that I use. There's nothing remarkable here, so I could really write the same thing as in Agda, as I write in Agda, and then elaborate it into a syntax which looks like this, which is a bit more explicit, because here I have explicit application and explicit EL and so on. Yeah, and I said strict positivity is enforced by the function space. So one might say that even now, already now, that isn't this definition of QIIT a bit circular? So what I said, the CWF with type formers U and EL and pi, it is a QIIT itself. So, and I want to define what signatures are for QIITs. So it's somehow that I already need to have QIITs to be able to say what a QIIT is, which is probably not something what you want. So, but there's a easy solution to this. So you can just church encode this theory of signatures, and then you have a you have the theory of signatures as a QIIT, and then you can use the theory of signatures to describe other QIITs. And I think this is the easiest way to bootstrap it. And in fact, there's this church encoding of Awody, Frey, and Spate, which gives you not only a recursor as the original church encoding, but also an induction principle. So you can also define functions by induction on these church encoded signatures. So obviously these church encoded signatures will live in a very high universe, one higher universe than in which you want to eliminate into, but this is only what you have to put up with when you if you really want to bootstrap the whole theory, and you don't want to say that so when you want to avoid this circularity. Okay. So what is the semantics of this theory of signatures? So we now know what a signature is. We've seen how to write down a couple of signatures, and how do we say that? What we want to say, eventually say, is what does it mean that a model of type theory or a CWF supports signature? So something that is well known is that if C is a CWF, then in the pre-sheaf model over C, so in C hat, we have these U circle and ES circle type formers, which are just types interpreted as types and terms in C. So this is the idea of two-level type theory, where you work in a pre-sheaf model over a model of type theory. And in this pre-sheaf model, you have access to things in the original model. So I will use this U circle and the ER circle, and we also have a pi circle, which has a similar shape as our pi type, that the domain is in U circle, the codomain is an arbitrary pre-sheaf, and it is also a pre-sheaf, so or a type in the pre-sheaf model, and it is interpreted as context extension. So so for any CWF in pre-sheafs over that CWF, I can talk about types in C by U, terms in C by EL, and context extension in C. So with that, I have this kind of restricted first order pi type. And also if C has identity types, then this U universe is really closed under identity, similarly for pi types and other type formers. So now from pre-sheaf explicit CWF combinators, what I will do is like this Orton and Pitt style is to use Agda's syntax for convenience to work in C hat. So now I have this U circle, which is a type, ES circle, which is a family of types over U circle, and then I also have this pi circle type. And here for the reminder, I wrote here what they are interpreted with in the pre-sheaf model. So now inside C hat, or in our Agda syntax, we can define models, simple models of this theory of signatures. So to define a model of the theory of signatures, I need to give all the components of this theory of signatures. So, and this is the standard model, where or it's also sometimes called the set model. So contexts are just sets, types are families of sets, terms are dependent functions, and here I interpret my extra new type formers of the theory of signatures with this U circle, ER circle, and pi circle. So let's see what happens if I apply this to a particular signature. So this is the signature for natural numbers. in the most formal way described. So if I interpret this in the standard model, then this is what I get. So an n in U circle, then an EL circle of n for 0, and for successor I have this function from n arrow circle, ER circle of n. And if so, this is what it looks like inside the pre-sheaf model, or in the internal language of this pre-sheaf model. And if I look outside and check what this is interpreted externally, then I see, because this U circle is interpreted as types in C. So what this standard model gives me is that I have a type in C, I have a term of that type, and I have a term which gives me an element of that type, assuming an element of that type. So this is exactly what it means for the model C to support the constructors for natural number, or the type formation rule for natural numbers, and the two constructors for natural numbers. Okay. So, and this standard model, okay, so that gives me the constructors, but I also want to talk about the recursion principle or eliminator. So we can extend the standard model to the graph model, where a context is interpreted by a set. I call it A, so this component is gamma A, because these are algebras. So if gamma is the signature for natural numbers, then gamma A will be the natural number algebras, and gamma M will be natural number morphisms. You will see it on the next slide. But this is, if I just look at context, these are graphs, because I have a set and a double index set over the other set. So these are the edges and these are the vertices. And I can extend the interpretation of U, EL, and pi to this graph model as well. So the interpretation of U in the graph model will be functions between the two different codes. So I have a code A0 and I have a code for a type A0 prime, and this I will interpret it with a function between these. And for EL, I will interpret it with an equality. And pi is interpreted, for pi I just recurse and use quantify over the first type, and I just recurse over the B. And here I apply the two types, or the two functions that I used, once for this input, and once I apply the function which I obtain from this A, because A is in U. So this seems a bit complicated, but let's see how it works. So given the natural number signatures in the graph model, this has two components. So we have algebras as before, which is the same as before. And then we have, for any two algebras, nzs and n prime z prime s prime, I have the following set. And this is a homomorphism between the two algebras. So we have an n bar, which is a function from n to n prime. This n bar respects 0, and this n bar also respects successor. Okay. And if I look at this externally, then I get if I look at this externally, I get an external notion of algebra for any model, and an external notion of homomorphism with definitional equalities. So this is a definitional homomorphism for any two algebras. By definitional, I mean that these equalities are really the definitional equality of the model C. So and with this, I can already describe what it means that model of type theory supports constructors for the signature, and also the recursion principle, or the recursor. And I can extend this graph model to the AMDS model. So in the AMDS model, I don't only have algebras and morphisms, but also displayed algebras and sections. And for context in this AMDS model look like this. So I have a set of algebras. Then for any two algebras, I have a set of morphisms. Then for any algebra, I have a set of displayed algebras over that algebra. And then for any algebra and displayed algebra over it, I have a set of sections of the displayed algebra. This model construction is an inverse diagram model, so category theorists probably like to describe it that way. But let me show what exactly this gives, for example, for natural numbers. So algebras of natural numbers, we know what they are. Homomorphisms are just homomorphisms of natural number algebras. And the displayed algebra over a particular algebra, this n dot with these three components as well, it's the input of induction for natural numbers, or it's the arguments of the eliminator for natural numbers. So you can view it as a predicate or proof relevant predicate over n, and we have a witness for 0, and for any n we have a witness for successor of n. And the section of a displayed algebra is a dependent variant of the homomorphism. So it's a dependent function which also respects the operations. So now with this AMDS interpretation or AMDS model, I can say what it means that a model of type theory C supports a QIIT. So for any signature omega, I get these 4 components in a set, which is a type in the pre-sheaf model in the empty context. So this, or I just say I get a pre-sheaf. I have this dependent pre-sheaf, or a type in the pre-sheaf model indexed by 2 algebras. Then I have displayed algebras and sections like this. And to say that CWFC supports this omega, this is how I say it. I say that there's a we have the constructors. So that's a term in the pre-sheaf model, or a global section of the algebra interpretation, together with the eliminator. And this eliminator says that for any displayed algebra, I get a section. And with this, I specify the computation rules as well as of the eliminator with the definitional computation rules. So this is how I say that the CWFC supports a closed IIT. And it will look exactly the same once we add more type formers to the theory of signatures. So up to now, I showed what it means that a C has closed IITs. So the main points were that the signature is a context in this theory of signatures. Then we have this AMDS model, which is an internal model of the theory of signatures to any category, for any category C, internally to C hat, so pre-sheafs over C. And these use these extra type formers, which we get in 2-level type theory, or which we get in any pre-sheaf model. And then externally we get the proper notions of constructors and eliminators. So let me show you how to extend this to other to a larger class of QIITs. So first, if we want to add external parameters, then we have a new function space, this pi hat, which is indexed by elements of U circle. So you remember U circle were types in C. So this we can index our types in the theory of signatures by types in U circle, and we also have an application for this. And in the standard model, I interpret this new pi hat type former exactly the same way as the original pi type former, so with context extension. So let's see what happens now. So we can, for example, specify vectors. If C has natural numbers, then I have a code for natural numbers in this U circle, because types of C go into types of C hat. And then I can specify I have vectors which are the sort of vectors is indexed by natural numbers. I use this pi hat, this arrow hat here. I have the nil vector, and here I use so a term of C leaks into the signature. So this 0 is a term in C, and that's why I can refer to it when I talk about an element of this element of a type which comes from C. And I can also describe cons for vectors. So whenever I have, and here I need to use this pi hat function space and the ordinary pi function space as well. So with pi hat, I add parameters to the type, and with pi, and with the ordinary pi, I can add recursive parameters of that for the or recursive arguments for a constructor. And once I added external parameters, I can, for example, describe the Chapman style syntax of type theory with an infinite hierarchy of universes. I need natural numbers from C to describe the infinite hierarchy of universes. So that's why I need these external parameters. Then if I want to add equations, I can choose to use an identity type with reflection. So I just add an identity type. So I have an equality of types in U, and this is a large type, and I also have equality reflection. And in the standard model, I just interpret this as the equality of the Prisheaf model. And if I add this type former to my theory of signatures, then I can specify all of the strict QIITs. So by strict QIIT, I mean a QIIT in which all the equalities are satisfied definitionally in the model. And I can describe the integers that I showed previously in Agda. I can write down their signature this way with this. Here I'm using this new equality type with equality reflection. So I have equality reflection in the Prisheaf model for the ordinary equality type in the Prisheaf model, and I'm just using that. I will just use that to interpret reflection here. But I can also go a different way and not take this EQ type. So, oh yeah, sorry. So I can also now describe type theory as a QIIT itself. So I can go a different way and not describe EQ type, but usual identity type with the J elimination rule. So here I don't need equality reflection, but for this I need to require that C already has identity types, and then I just interpret this identity type as the identity type in C. And with this, we can specify all. If I have this identity type, I can specify higher inductive types. So you can look at this paper for a description of this. So, for example, I can describe the torus, which has the torus for the sword. Then I have the constructor B, and I have two equalities between, or two elements of the identity type between B and B, and then an identity between these two identity types. And I'm using J here inside the signature to describe transitivity of equality. So I can also write higher equalities, and if you look at this AMDS interpretation of these equations or this identity type, you get the expected elimination principles, the expected recursors, and so on. And one more thing, so far all of our QIITs or HIITs were finitary. So there were no infinitely branching trees, for example. And I can add a new operator or new type former, which allows infinitary operations. So here I say that this is a closure property for the universe U. So up to now, the universe was empty. No, in fact, it's not completely true, because the previous identity type was also in the universe. That's how I could iterate it here. So and also these infinitary operators, they are also in the universe. So in the universe, I can index terms in the universe by a type in C, so an element of U circle. And if I want to interpret this, I need, just as for the identity type, I needed C to have identity types. For this infinitary pi or pi tilde, I need C to have function space. And then I just interpret this pi tilde with that function space, which I have in C. And now I can, this is a description of infinitely or natural number branching trees, infinitely branching trees. So I have a type for a T is in U, then I have a leaf and I have node, and here this seems a higher order signature because there's an arrow left of an arrow, but this is this infinitary arrow, so this is this special tilde arrow which I'm allowed to use on the left of the arrow. So here I have an recursive occurrences of T, and I have natural number many of them. So now we can, if once I've added this is my last new type former. So once I've added these infinitary operators, I can describe the theory of signatures itself as a QIIT. I can describe the real numbers or the partiality monad, which are all infinitary ones. So in summary, I had the theory of signatures is a CWF with these type formers. So U and EL was a universe, pi was for recursive arguments, pi hat was for parameters from C, from the CWF that I'm talking about. Then I could have extensional or intensional identity types, and pi tilde for infinitary parameters. So now I turn to the next topic, initial algebras. So in fact, okay, sorry, let me just skip this. So if C is a model of extensional type theory, then this AMDS model, which gives me algebras, morphisms, displayed algebras, and sections, we can extend it to a much larger model. So we can extend it to a category model. So for every signature, we get now we don't only get a notion of algebra and morphism between them, but we have a category of algebras for that signature. And moreover, it's a category with extra structure. It's in fact a CWF with sigma and equality, extensional equality, and a constant type. So a constant type, this K type former just turns a context into a type. And then substitutions into that context are isomorphic to terms of these constant types. And this model works for this, we call it finite limit CWF because Dibier and Clérambault proved that CWF with this structure is the two categories of CWF with this structure is equivalent to the two category of finite limit categories. Yeah, and this finite limit CWF model works for all type formers for the extensional version. So not for identity types, but for extensional version, but all the type formers. And this works. Sorry, it also works for the usual identity types, but C needs to be a model of extensional type theory. So this doesn't work for higher inductive types. You can only describe things in the model of ETT. So for each signature, you get finitely with CWF. So we have a category of algebras with lots of extra structure. And this extra structure is enough, for example, to prove equivalence prove that induction and initiality, so a recursor with a uniqueness principle, is equivalent to the elimination principle. So in this model, so now we work in, now con is context in this model. So con is a CWF with all of this stuff. And this is, we describe the recursor. So what does it mean that a theta, so an algebra, a context, which is an algebra. So what does it mean that theta has a recursion principle? It means that for any other context, there's a substitution into that context, right? Or you could say for any other object, there's a morphism to that object from this theta. And moreover, this is unique. So these first two assumptions, they say that I have this is how I describe that theta is initial, and the theta has an elimination principle. It is described by saying that every displayed algebra over theta has a section. So for every type over theta, I have a term of that type. And there's a very simple argument with which you can prove that these two things are initial in a kind of type theoretic manner. You need to use this is how you describe this is how you obtain the elimination principle from recursion, and you also need to use uniqueness to make it sure that it's well typed. And this is how you can obtain recursion and uniqueness from the eliminator. And here we use this equality type and the constant types as well. Another result is that that again, if a model of ET, again, this works for in the extensional setting. So if a model of ETT supports the theory of signatures as this QIIT of the theory of signatures, then we can show that it supports all QIITs specified by that theory of signatures. So for example, if a model of ETT supports the theory of signatures with U, EL, and pi, then it supports all closed IITs. And the idea of obtaining all QIITs from only the from one single QIIT, the theory of signatures, is close to Church encoding. So for example, if we have the theory of signatures, then we can define natural numbers as follows. We just say that natural numbers are of type, are a term of type n in this context, in the natural number algebra context. And then 0 is just the variable z, and successor of a t is just applying the variable s to the term t. And that's how I obtain numbers. And it's very easy to see that if you have this, you can implement the recursor, for example. You just interpret the natural number in the standard interpretation, or the algebra model of the theory of signatures. And then if you look at what this becomes in the algebra interpretation, it just becomes the recursor for the particular natural number that I started with. So it says that if for any natural number algebra, I get an element of that natural number. And an interesting point is that if you interpret not in the algebra model, but in the algebra morphism model, or the graph model, then you get the Awody-Frey-Spate encoding of, because this is the usual Church encoding of natural numbers, but you can also get this nicer encoding, which gives you the eliminator. But we can also define the elimination principle with this construction. So if we have this result that if model of ETT supports the theory of some particular theory of signatures, then it supports all QIITs. And we can use this result for different variants of the theory of signatures. So for example, the theory of signatures with only U, EL, pi, and pi hat, which is finitary IITs, so finitely inductive types, it can be defined in extensional type theory with index W types. We don't need any quotients to define this theory of signatures because it only has neutral terms. So in this case, this pi and this pi hat doesn't have lambda; it only has application, and that's enough to describe signatures. So because it's a theory with neutral terms, then you can just define it. So we know that if ETT, so we know that finitely inductive types are don't extend type theory. They only get they don't extend type theory with W types. We're also working on showing that the setoid model of type theory supports the theory of signatures with all different type formers. There's a type abstract about this. And we could also, another way to use the initiality proof of and formalization of Bruneri and Deber is by they have a they formalized that if a model of type theory, if a model of ETT supports quotients and propositional extensionality, then they formalized initiality for type theory with U, E, L, pi, and ID. And I suspect that if we restrict their formalization to the restricted version of pi that we have, then we obtain the theory of signatures. So then we obtain that we have all closed finitary QIITs for any model of type theory with these components. There are also some negative results. So we know from Lambsdane and Schulman that certain infinitary QIITs cannot be defined in extensional type theory and quotients. And there's also work on a more direct reduction. So this kind of reduction only works in extensional type theory. It doesn't give, it only gives propositional computation rules, for example. And we hope that we could do a direct reduction, so not to reduce all QIITs to the theory of signatures, but to reduce all QIITs uniformly to W types and quotients or something similar. And then we expect that we can get definitional computation rules for these. But currently, we only have results in extensional type theory. Okay, so let me talk very briefly about categorical semantics for HIITs, which wasn't done by me. It was done by Capriotti and Sattler. So they have an abstract at this year's types, which unfortunately didn't happen. But the abstract is very nicely describes this their strategy. So they construct a higher category of algebras from a signature. So they use two-level type theory to talk about higher categories in type theory, and they support all the type formers that we have. They also define displayed algebras and sections, and then they show the equivalence of initiality and induction in this setting as well. So for each HIIT signature, we have a higher category of algebras where initiality and induction coincide. But we don't yet know. So for general HIITs, we don't yet know of any general results about existence of initial algebras. We know about existence of initial algebras for simple classes of higher inductive types, not for higher inductive types. So we described what it means that a model of type theory C supports a QIIT, but the QIITs are particular kind of inductive types. So they are inductive types, but in type theory we have other types. We have pi types, sigma types, universes, co-inductive types, and so on. And does this theory of signatures approach help us in any way to describe these other type formers as well? So we can just say that type theory is a QIIT. So we can define what CWFs are in a QIIT, and then say what it means that we have pi types and sigma types and so on. But then the semantics that I showed you, it has a bit of an overhead, because then we don't simply describe CWFs but with a signature. But what it means that a model of type theory has an internal CWF and extra structure. But okay, maybe this is not a problem. But a more serious issue is that there's lots of boilerplate involved. So we would need to, when we describe type theory as a QIIT, we need to write all the substitution laws by hand. And there is an old solution by higher order abstract syntax, which was analyzed by Martin Hoffmann in the 90s with pre-sheaf models. Which avoids having to state the substitution laws all the time. So a possible solution, and there's also Paolo Capriotti's rule framework, which he presented at Types 3 years ago, which is very similar to this theory of signatures approach. So there you have a theory of it's like an extension of the theory of signatures. You have extra rules, you have extra type formers, which help you describe other type formers as well. So a simple way to extend our notion of theory of signatures to type theory signatures, where you can also describe pi and sigma types in a convenient way, is that saying that, okay, we have the current theory of signatures, which had types. And we will call these types Ti0 from now on, so some kind of small types. And we add a new sort of Ti1 types, so kind of higher level types. And we can also convert Ti0s to Ti1. And basically we add this type. So instead of saying that we have arbitrary pi types, for example, we add this Ti0 and Ti1. And this is how we enforce that our new kind of extended signatures are strictly positive as well, and then that we can get a category and good semantics for all of this. So, and we also, just as we had U and EL, now we have Ti1. Now we have Ti0, which behaves a bit like U, and we have this upper row which behaves a bit like EL, and Ti1 has a function space where the domain is in Ti0, so it's again the same pattern, and we also have a extensional identity type of Ti0s, which is also in Ti1. And now if we have this more general notion of theory of signatures, the signature is again a context. So let's see how we can describe that. We have pi types using these extended signatures. And here we don't need to write substitution laws. So this is just a signature of pi with beta. So we have this pi1. This we say that we have a, so this is like a higher order signature for pi types. And again, the higher orderness is like second order, because we are allowed to write an arrow on the left-hand side of an arrow, but that arrow needs to be a zero arrow or an arrow without any number, and the big arrow is always a one arrow. So here you write, so pi is for any type, and a type over that type, I get a new type, right? A type which can refer to that type. That's how we interpret this. And then for lambda, for any type A, and the type over that type B, and then for any term, EL is interpreted by term of the second type, I get a term of the pi type. And then application goes the other way, and then with the equality I can describe the with the identity type format I can describe the equalities as well. And this is work in progress, but I expect that this way you get the notion of algebras, morphisms, and so on are the expected ones that you get using this method. So, and you can convert between type theory signatures and QIIT signatures as well. So from a type theory signature, you can obtain a QIIT signature. And what this conversion does is it adds all the extra substitution laws, so it becomes much more explicit. But the nice thing is that then from a type theory signature, you obtain a category of models, and you also have a initiality proof for that type theory. You can also go the other way. From a QIIT signature, you can obtain a type theory signature. QIIT signature only describes the constructors, but if you describe it as a type theory signatures, then it adds the elimination principles as well. So the recursion or the induction principle. And then you get a more syntactic description of what it means that a type theory supports a certain QIIT. And this can be generalized to arbitrary signatures with binding. So here this setup that I showed at the previous slide, it only works for kind of type theory signatures where you have types and terms, but no other sorts. And it also doesn't work for cubical type theory because you only have the usual context extension and you cannot extend the context with the interval. But in a more general settings of signatures with binding, you can describe all other all languages with binding, basically, which type theory is one special case of. And for this, you need to have a sort of, so you have to distinguish a representable type. So presheaf has norm. So types in a CWFC are just a presheaf, but terms are not not only a dependent presheaf over the presheaf of types, but they are also a representable presheaf, dependent presheaf. So a representable type in the presheaf model is an ordinary type in the presheaf model together with context extension, basically. And once you have this, you can use the pi types in the theory of signatures, and you can describe higher order signatures this way. And yeah, this is ongoing work. So that's all I wanted to say. As a quick summary, I just recap that so a QIIT or an HIIT can be described as a context in a well-chosen type theory of signatures. And then the semantics for the QIIT can be described by presheaf models of the theory of signatures. And the results that I mentioned was that in ETT, if you have the theory of signatures, you have all QIITs. And it seems that we can extend the theory of QIIT signatures to a more general notion of signatures with binding or to type theory signatures. Thank you. And sorry for the 5-minute overtime.
Great, thank you very much. So we'll do our usual silent visual applause. And then we open the floor to questions. Please just unmute your mic if you have a question.
I have a conceptual question, if that's
Okay.
all right.
Go ahead.
If we phrase this in slightly more category theoretic language, is the sort of general idea that if you start with a category with families, as long as you have some sufficient structure like your pi types, sigma types, the universe, etc., you also have a definition of a category with families internal to a category with families, and this automatically has certain type formers like pi, sigma, etc. Is this the right way of looking at it?
I think, I mean, do you mean this FLCWF semantics? So so for any such signature, you get a an internal CWF with sigma and constant types, but not much more. So you don't get pi types. But I'm not sure if I understand the question correctly.
I was just listing random type formers, but I just wanted to make sure that internal CWF was the right way of thinking about it.
Mm-hmm. Yeah, so internal, you want to talk about things or type formers for a model of type theory C, then you work in presheaves over C, and there you describe internals. There you describe internal CWFs in presheaves over C. So internal to presheaves over C, and that's where you can argue about QIITs in C or HIITs in C or other type formers in C.
Okay, thank you. That's helpful.
Okay, are there more questions? Mike is unmuted. Do you have a question or comment, Mike? Are you having trouble with your microphone?
Yeah, can you hear me now?
Oh yeah,
Yes.
there we go. Yep, go ahead.
Sorry, is this better? Is that okay?
That's fine. Yeah.
That's fine. Okay, great. Sorry. Your theory of signatures is, you said it is a particular QIIT. I think I didn't quite understand. I don't quite understand how important it is. It important that QIIT has an elimination rule? Like, are you mapping out of the theory of signatures using its universal property, or is it just that sort of it describes it describes what the syntax of a signature on which you then only describe what the algebras are? Does that make any sense?
Yeah. So just to give a semantics of QIITs, it doesn't need to have an elimination principle. So to obtain a category of algebras, you don't need an elimination principle. Where we do use the elimination principle is in the proof of initiality for existence of QIITs. So there, when we want to show that we can show that any particular QIIT exists if we have the proper elimination principle for the QIIT of the theory of signatures. So, and there we need the full elimination principle.
So you mean to show the initiality of syntax for for a theory containing that, you need elimination principle? Is that what you said?
Can I try? I don't know. The point is, you define the theory of signature, which is a particular QIIT, and now you want to prove that from this you get all QIITs, and for this you need the dependent elimination for the theory of signature.
Oh, I see. Okay, so what you get is that if a particular model has QIITs for the theory of signatures, then it has all QIITs.
Yes.
But you can say what it means for a model to have a particular QIIT without knowing that the theory of signatures has an elimination rule.
Yes.
Okay,
yes,
got it.
Exactly.
Thanks.
Yeah.
Okay, anybody else?
Yeah, can I say something? So I'm looking forward for this reference you give for the higher theory, I mean the theory of higher inductive types, because actually this sort of, which looks a bit like a triviality, namely that initiality and induction is the same, or initiality and elimination is the same. Turns out that for higher inductive types, that can be actually quite tricky. We looked at some examples, and at least it seems to be very laborious to do this. So having this these properties of higher inductive types is actually quite useful and has interesting consequences. So I'm looking forward. I hope that they're writing a paper. I mean, I don't know. I think Christian's always busy with lots of things. But yeah, that'd be nice.
Okay. More comments, questions?
Maybe I can ask one question. You seem to, so the church encoding came up naturally, but sometimes there are other encodings like Scott Mogensen or Perigo and others. Is there a reason, like you kind of landed exactly on church, and is there a natural way some of these other encodings might arise from these considerations?
I don't really know the other encodings, but I mean, I was quite surprised when it turned out that this kind of term model construction, when we construct an arbitrary QIIT from the theory of signatures, it generalizes church encoding and also this Awadi phrase paid version of the church encoding. So it might also be a generalization of other encodings. So here what you need to do is to look at a model of the theory of signatures, which gives you that particular encoding, and the standard model gives church encoding, and the graph model of the theory of signatures gives this Awadi phrase paid encoding.
Can I comment on Scott Mogensen encoding? So I'm not sure if that works because I think Scott Mogensen encoding requires recursive types in general, and it's kind of it's not a conventional thing to support arbitrary recursive types in a model of type theory.
Sorry, another thing to add is that this is a predicative church encoding. It's just you add another level. It's not the impredicative encoding.
But it's also possible to do the impredicative encoding as in the Awadi phrase paid paper the same way, but then we just have to assume that we have an impredicative universe in the C model.
Yeah, but so in my talk, I didn't use impredicativity or anything like that at all.
Okay, still have time for more questions if there are any, or comments.
So I think, I mean, what Ambrus said in the beginning maybe needs to be emphasized, that there really sort of a level of encodings and the sort of logical framework style is the highest. And logical frameworks, and we have quotient inductive types, inductive types, inductive types, and it's interesting to look at these reductions at the same time, but in a way you want to do the reduction once and forever, and then you want to work in the higher language. I mean, okay, in the language which is appropriate for what you want to do.
Okay, anybody else? Okay, well, let's thank Ambrus again. Okay, and HIITs will return in 2 weeks with Nima Rasak as our speaker. So I hope to see you then.